Good morning, everybody, again, and welcome to Physical Science 1 for the fall of 2020. The class will be held online, basically. You have access to the Canvas, basically, material. And we will be meeting on a regular basis during the allotted time, which is 8 o'clock from 8 to 9:25 every Tuesday and Thursday. And the attendance is required. You don't have to attend it live, but you can always watch the recording. There will be some discussions after every session. Not the first one, at least not the first week, but from this point on, you will have assignments discussed in the live session. And those assignments, basically, you answer them in the discussion session, basically. So you would attend the class, and while you're attending the class, you can basically take notes. At some point, I would say this is one item for the discussion. You will have an answer during the live session. If you cannot make the live session, you can always go to the recorded version of that live session and basically see the same thing. Come to the discussion point, you're going to say the answer to the item, whatever that answer was. So that shows me that you're following. The reason why I did that is because in the past, I taught several classes in the spring for online, and I was doing live sessions then, but then we were told you really have to be flexible for the people who are working and so on and so forth, which is fine. So in the summer, I did the recorded versions. I do surveys, and you will be also faced with survey at the end of the class. And the students at the end of the survey really like the live sessions better. So they are more interactive. You get a chance to ask questions. You get a chance to basically interact with the materials more. And research has shown that people learn better when they actually do, not just by watching people do other things. You watch something, especially a class or a course online, being recorded. After probably the first 5 minutes, you lose focus. So it's better to be doing things while you're learning. So that's what I'm striving to do. And I'm hoping that you guys help me in the process. Right now, we have a little over half the class. We still don't have everybody on attendance because they know that. So I'm giving this leeway for this week, but next week, again, the live sessions will be graded, and I'm hoping that everybody will participate enough in this classes. Any questions before I start? Because what I'm planning to do today is discuss a little bit of the syllabus, and then start with the class. Okay. Okay, when you log in to Zoom sessions, please put your real name in there. I know some of us have wonderful dogs and cats and so on and so forth, and we like to put their names instead. But I really need to know your name so that when I refer to the discussions, I know who the person in the class is. I don't see this a problem for this class. It seems like everybody has their names, but sometimes people have tendency to put other names in there, okay? Because if I don't recognize your name, also I may block you there too, which is not nice. So, if you guys don't have any questions, let me go into sharing my screen. While I'm in the sharing mode, I will not be able to see the chat session of what's going on. So I would need to ask you every time I go to a sharing mode, to have a confirmation, a verbal confirmation from one of you guys that it's okay, because sometimes I'm sharing screen and I'm talking, and after several minutes, nobody is looking and nobody is seeing what I'm talking about, and that's not good, because somewhere midway, I'm trying to make a point, and the point is basically not made because the screen is still the old screen. So while I'm sharing mode, please let me know that everything looks fine, that you guys are looking at the same thing I'm looking at. So right now I'm going, actually, before I do that, let me make sure I am in the right place. This is Physical Science 1. That's what I'm supposed to be. And so let me go back into the Zoom. Okay, share that. Okay, so you're supposed to be looking at PHS-1 F20, which is your class, correct?
Correct.
Very good. Thank you, Naomi. So basically, this is the class. This is where it's going to be held. It's you have received at least 2 emails from me in the past, one last week and one on Sunday. Basically introducing the course, the links, the stuff that you need, the materials that you need for this class in terms of textbook and things like that. So I hope that you have had the chance to go through those things and ready yourself for it, and you know exactly which class you're supposed to be online for when it comes to this class. Now, there is at least one person I know of today, but I know there are more people actually who are late ads, and they may not have received those communications first. And then the other thing, there is an that is due by this Saturday, the initial reply or the initial response, and then the peer reply, which is due by next week. So they need to be made aware of. Hopefully they will have access to the resources as you guys did already, and be ready for that stuff too by this weekend. Okay. So that's one thing. And I introduced myself enough in there. I have been teaching physics and physical science and astronomy now for several years. And I think I know the stuff. So hopefully you guys should not have a problem with the content. This course itself has basically several components in it, so that you know. It's physical science, which means it's physics, chemistry, geology, and astronomy. So that's basically what the 4 components of this class is. That's why we have several tests. Every unit has its own exam. Okay, it has its own part basically that we're going to be talking about and testing on. So we need to have the foundation of all sciences, which is physics. Physics is the one that started the scientific method, by the way. It was not started in biology or any other field. It was started by a physicist in the Middle Ages. His name is Alhazen. And then later on, it was adopted by a lot of other scientists. People before him, they were doing scientific method, but not really properly documented. So that's basically what we're talking about. Then later on, it spread around. Chemistry is really actually a branch of physics. It's applied physics no more. Geology, it has a lot of applications from physics and chemistry, and basically some of its own techniques that are related to rocks, rock formations, and also plates and plate tectonics, especially as it relates to Earth. And also it turns out what we learn about the geology of the Earth has applications in terms of what we know about other planets too. So when we study, for example, the solar system, we learn of how, for example, the surface of Mars is structured, how is it impacted by different internal processes and external processes. And the same thing applies for actually the moon and Mercury, and geology of Mercury and the moon are more or less similar. Venus is completely different than the other planets because of the fact that it's super hot on its surface. So it has its own geology also. For planets, we don't even know that they have a surface. I mean, for Jupiter, for example, there is no evidence that the planet has any kind of surface, so we don't understand its geology at all. So that's some of the things that are related in terms of geology. That's not the only things we're going to be learning in terms of the astronomy components. Actually, we'll be talking about stars and galaxies and things like that. So this is a big task. We're going to learn everything there is to know about physical science. Of course, we don't have enough time to go in depth about every topic, so I'm hoping to touch on some of the basics. And the basic ideas are the following, if I can find them in here. There's 3 points. Okay. Those are the main things. Those are the objective. This is our student learning outcomes. This is what you hope to achieve at the end of this class. Analyze the unifying principle which underline the various branches of scientific endeavor. So basically there are some general themes that we need to touch on and understand exactly what they mean, and be able to distinguish between what is a scientific fact and what is a myth, if you wish, or falsehood. So that's basically, we have to make that distinction. Identify the basic physical concepts necessary for understanding technology and natural environment. Guide the students to understand their role as members of society, becoming increasingly dependent, as we are becoming basically increasingly dependent on technology. As a matter of fact, this is an example. We're doing class. If it were not for technology, we cannot do this class. So technology basically is not science. I mean, it's an applied science, if you wish. It's the tools that are developed using science. So those are some of the distinctions that we need to achieve by this one. So the main thing is those over the big picture, basically, that's what we're going to try to achieve. Okay. You have also in here what we will be doing week by week. So I'm hoping that this week we would have covered these two topics. I already put the stuff for chapter 1. Chapter 2 should be available today. So you'll have it also on Canvas, so that by the end of this week, you will have enough materials to cover those two chapters and so on and so forth. And we move fast with the material because we have a lot of topics. At some point, we're going to skip chapters. And like, for example, in geology from, what is it, chapter 20, what is it, 4, 23, no, 24 and 25 are skipped. Then we are going to get into the solar system and the galaxies and the structure of space-time, basically, and that is general theory of relativity and exam 4. The final is comprehensive. One of the things I have to warn you up front is I don't make up exams. So if you have a deadline for an exam, please take care of that exam right away. After that, you're going to receive a 0. Okay, so that's one of the things that I always warn my students beforehand. And because of that, then I drop the lowest grade. So that's one of the things that I do. There's a makeup just in case if you have a big emergency and you cannot make it, you know that that's the exam that you're going to be dropping. Okay, or that's the task that needs to be dropped. Now, the final is by itself, so it cannot be dropped. Okay, so it's worth 20 points. So that's something that is you need to be aware of. So that's basically in a nutshell what this thing is in terms of the course policies. For those who already have a chance to go through the first module, the first unit of this course, the first thing that you want to do is go through the community rules on how you address people, how you basically be mindful of the fact that we are not in class and we're communicating electronically, and there are some etiquette that needs to be observed while you're doing that. In terms of submission, everything is going to be online, so all the things that you're going to be submitting are going to be online. So if in case there is a project and there is something that needs to be uploaded, you need to scan it. And that's it. The final is on Thursday, December 10th. So you have the date for that. And that's basically in a nutshell what's going on. There is already this assignment. Please remember for this assignment to include a picture of yourself. I think there were a few people, I'm not sure if it's from your class, but from another class that they submitted a lot of their initial replies or initial response without their picture of their own. So it's very important to include a picture of yourself so that we know who you are, basically to have a chance to basically to address you respectfully, of course, and so that you know who we are too as a class, not just as individuals. So we have to know each other basically and to work with one another. And the purpose of the first assignment is actually to establish that rule of communication and working together. Next time we meet, we will have an assignment where we will break actually into rooms and you're going to have a chance to work with your peers. By then, hopefully you will have your camera working so that your peers actually can work with you individually in a small groups of 5 or 6 people working together on a specific task that is related to this class. Does this sound right?
I have a question.
Yes.
For the picture, do you want a separate picture aside from our profile picture?
It doesn't matter as long as it's a picture that we can see your face in. Everybody can recognize the other person, so that if I meet you in the store, at least I know who you are. Okay. Okay. No, not necessarily. I'm joking about that last part. Basically, so that we have face to face, because there is actually a problem. Sometimes people, when they're dealing with a name, they lose the fact that that's actually a real person behind that name, and we want to put basically a human element to who we are, so that we have that basically peer communications and working together and understand that we are here together to work on this class and learn, and basically hopefully we will be valuable members of society, which is one of our objectives, and contribute to society, and we know each and every one of us. So that's really important, okay? As long as it's a picture that can depict you, that would be great, okay?
Thank you.
No problem.
Hello.
I'm sorry?
We have a question.
Yes.
I'm registered for this class, and my daughter has been emailing you to try to get into the class.
Is that Sarah?
Yes.
Okay.
So I don't know if you ended up, and you sent her an ad code, but it wasn't working because they had closed the class.
They closed it, but for some reason today, at least another person was able to add. I think they reopened it. They sent us an email yesterday that there are glitches in the system, and they're trying to work very hard to fix them. So, okay.
So should we retry the same ad code?
Yeah, try the same ad code. If it doesn't work, I'll send you another one. I think I have enough of those. Okay, and the same thing applies for somebody else who sent me an email also about the ad code saying that it was not working too. So if it still doesn't work, I'll send you another one. Okay?
Okay, perfect. Thank you.
Okay, no problem. Okay. So we're going to start the materials and let you guys have another question, which is, everything should be in there. And if you have a question about the syllabus, please do ask. This is basically where you're supposed to be starting at. The main thing that you need to do, as I mentioned in this intro, is the models, basically, when it comes to time to class. I'm right now in the instructor mode, so if I go into models, you will see things that are not ready 100%. So I'm not going to do that, but if you go into the models, you will see the things that you're going to do for this class, okay? If you happen, and I'm talking to Sherry specifically and Sarah, if you happen to be on the same computer working together, when we go into breakout sessions, we may have okay, that's fine. Okay, so you guys can be in the same group basically later on, but it's not today, okay?
We have two separate computers.
Okay,
She'll get on hers once we get her in the class.
Okay, very good. Thank you. Okay, so let's stop sharing the screen and go into another screen. If I can find it. Okay, so it should be, what is the share? Okay, so this is the first basically chapter for this class, and it's basically we're introducing motion. And the question that is asked by, that we ask all the time, basically when starting physics, this is the first part of the class, the first unit of this class. What does physics study? Does anybody know? What is the fundamental question in physics? What have you heard? You can type the question, by the way, you can type the answer in the chat session if you like, okay? By the way, if you're not familiar with Zoom that much, there is a chat in the bottom of your screen, and there is also participants. If you click on participants, you will have more interactions. You can say yes or no and can do other things in there. Raise your hand and do other things. Okay, so the question is, what is physics?
Quantum mechanics?
Wow, that's quantum mechanics is physics, true. But what do we study in physics? Anybody?
Things like gravity and like momentum.
Gravity, momentum. That's good. So you guys know. Let me tell you in a nutshell what physics is, okay? What we hope to achieve from physics, okay? That's good, Joshua. How things work physically. Okay. Basically, the fundamental question that we want to ask is how to predict the future. Okay. It's about motion. We want to study the state of motion of an object. Given the current situations or given the history of an object, where would that object be in the future? That is really the most important question in physics. So we want to predict. So quantum mechanics, for example, studies the motion and the dynamics of elementary particles in the case of the atom, for example, and try to answer those questions and things like that. So that's really how the fundamental question in physics is. So we want to know what happened to the object in the future. That's really what these things are. So radiation is an example. So some of you mentioned forces already, which is the causes of motion. Some of you mentioned, for example, momentum, which is another definition, if you wish, of motion. Study of matter, we want to really study the matter to break it down. It's really part of its, again, dynamics, trying to understand it, and we find that it has different components in it. So it's really the fundamental question, especially the word mechanics has to do with motion. Okay, so it's really the motion that is the critical part of physics. So we want to really study motion, and motion in a nutshell is velocity or speed. Okay, so the whole purpose is really to find the speed of an object. We know where it is today. We know where it is now. Where will it be at a certain time in the future? That's really the question. So if we can tally all the forces on it, and we know how it's moving, then we can always tell where it's going to be in the future. So patterns of motion, this is basically the topics that we're going to be covering in this. If I can click on this, we're going to be covering. So before modern day view of motion, there was people in the old days who were interested in the same topic. Aristotle was one of them who documented this idea. And his idea lasted for a very long time, basically for almost 2 centuries. That his idea, they lasted, that motion, basically, the hypothesis, he got all kinds of things. One of them is the tendency of object is to be at rest. Why? Because if I take, for example, this is my cell phone. If I put my cell phone anywhere and come back to it anytime in the future, the cell phone will be in its place. It's not going to change location. Do you guys understand that? So if I leave it in a certain place, it's not going to go anywhere. So the tendency of object is to stay in motion. The celestial object, like the moon and the planets, those are an exception. And the sun, those are an exception to this rule. And basically, that's what his ideas were. Of course, he's got some definitions for this vertical up and down motion and things like that. But again, all of them have this basic fundamental approach that if I take this cell phone again, for example, and try to push it on the surface, it's going to stop. Take any object, it doesn't matter. If you have even if it's I'm trying to pick up a pen, for example, in here, if you roll it, it's going to start moving, then it's going to stop. Why it's going to stop? Because he says, hey, it wants to stop because that's the state it needs to be in. So again, objects have tendency to be at rest. That's his approach to it. And you say, well, if I take this pen, for example, and roll it, it's going to stop. True. And if I'm going to take, for example, a spherical object and roll it, it's going to stop too, but the spherical object has tendency to stop further than this pen, for example, or that cell phone. So, of course, the question was asked to him and to his followers, and the answer was that some objects have better memory than other objects. Some objects remember quickly to stop, so they stop, like, for example, the pen. And some objects, they kind of have a very lousy memory. They forget, they continue, and then they remember that they have to stop. So it was added there to interpret why some objects don't stop and don't. And these ideas, which they may sound ridiculous nowadays, have lasted for a long time, far longer than actually Galileo's ideas that came later. So Galileo actually did an experiment, and we're going to talk about it. And he found that objects actually have tendency to keep on moving in the same direction with the same speed all the time. Okay, unless acted on by force And he showed that actually in the case of rolling balls, for example, the reason why they were stopping is because of the friction. If I make my surface smoother and smoother and smoother, they're going to continue moving forever. And the reason for that, or at least the property that gives them that ability to do so, is the so-called inertia. Object with a bigger inertia requires more force to be stopped or pushed. So that's basically to gain more motion or to lose motion. An object with more inertia, you need more effort to move it or to stop it, basically, whichever way you want to do. So that's basically the idea that came from there. Then we're going to talk about the net forces, because objects have tendency to gain or lose motion depending on the applied forces. I just said so that Mr. Galileo had shown that friction is the one that is responsible actually for slowing down objects that Mr. Aristotle was confused about. So it was a major discovery in the early 1600s that Mr. Galileo came up with this thing. And Galileo actually did a lot of experiments, and he studied motion, and he was able to measure the velocity with which objects move. And he was also able to measure the acceleration that we are all subject to as we're sitting right now on our chairs in our living rooms, namely the force of gravity, or the gravitational pull of the Earth toward the center. You guys probably heard of his story. He's so important in physics that he's got a special name. His name is Big Man G. So when you hear a physicist talking about Big Man G, that is Galileo, because he did so much for us. What do you think? We're going to talk about this one down the road, because we have some other problems don't really talk about. It's basically the way that he was measuring time, which is really a story by itself, because he's got so many things. Of course, he was, for his studies of the planetary systems and his belief that the Earth was not the center of the solar system or the center of the universe, he was prosecuted by the church and basically put into house arrest until he died. So that's one of the things, one of the saddest parts for his story. And it's still an ongoing story, as a matter of fact. Right now, there are a lot of people who are doubting this scientific, basically, approach, trying to fight, for example, this pandemic, and that's another thing for another day. But the point being in here is he suffered for what he believed is correct, which turns out to be he was correct. So that's really some of the things that we're going to talk about too down the road. Okay. So let's continue with these points that we need to cover in this chapter. Okay. Of course, we're going to be talking about equilibrium. And when we talk about equilibrium, there is something that needs to be distinguished between the two. I'm assuming that everybody is reading the book too, because there are some assignments that are going to be coming down from the book, and there are some quizzes. So hopefully everybody is not going to rely 100% of what we do on the lecture. And this is true even in the face-to-face lectures. So this is true even when we are in class. So you guys are going to be doing that on your own. So there are 2 points in here when we talk about equilibrium. There is the so-called rest equilibrium and motion equilibrium. Object can be moving and at rest in the same time, or moving at equilibrium and in the same time. So as long as it does not gain speed or lose speed, as long as its speed is the same, that is actually a condition of equilibrium too. Which I'm going to ask you guys a question in here. Are you guys, all of you, I know some of you probably are moving around, but the ones who are sitting right now, what do you think you are? Are you at the type of equilibrium where the object is at rest, namely has no velocity, or the type of object that is at rest, but actually moving at constant speed? So here are the 2 choices. Choice 1, equilibrium. Let me spell equilibrium correct. V equal to 0. That's the symbol for velocity. And type 2 is equilibrium, where V is constant.
Can we
Those
be both? I mean, I think we're at both because right now I'm sitting, so I am at rest. I'm not moving physically,
okay.
but my body in space is actually moving because the planet's moving.
Okay, okay. The choice is, first of all, either one or two. Okay, there is no third choice. This equilibrium. Okay, you can have a v that is constant or a v that is zero. Okay, you cannot have a v that is zero and constant at the same time, so that the constant is not zero. Because logically, v either is zero or v is not zero. So those are the two choices.
Okay, I'm picking that I'm constantly moving.
Okay, very good. So I see Rudy, I see Zina, I see also Jacqueline, Emmanuel. Everybody seems to agree, okay? However, there is a third choice, actually. I throw you up. We are not in equilibrium at all because of the same point that Sherry has raised, the fact that we're moving and we're going actually in a big elliptical path, and that big elliptical path will make it so that the velocity changes. So it's not constant, and the velocity is a vector, so it changes the direction. So that's one point. The other point also, we're moving. So I'm glad that you brought up this issue of motion. And we're moving actually around the Earth too. We started around 8 o'clock. Right now it's 8:30, about half an hour. The Earth is going around its axis 24 hours once. That means we're going 2 pi times the radius of the Earth. The radius of the Earth is about 6,400 kilometers. 6,400 times 2 pi, which is about 6. This 36,000 kilometers in 24 hours. That means in 1 hour, 36 divided by 24, that is about 1,000 something kilometers per hour. In the half hour that we set, we moved about 500 kilometers already. So that's a lot, okay? So this is basically to show you that we are not sitting still. And we're moving tremendously. If we try to do the same thing with the car, we're not going to reach that distance. I probably have made a little bit of a mistake in the calculation, 36. I probably will have to check the algebra correctly, but we have moved a lot. We have moved a lot. We have moved the whole distance in this half an hour, probably from here to somewhere in Arizona. Okay, so that's to give you an example of how much we have moved. So it's a big distance. So yes, you're right, but it's actually we're not in equilibrium because of the fact that our velocity is actually changing direction, at least changing direction. So the fact of the equilibrium, and here, let me go back into my slides. Yeah. So basically, so we're going to distinguish these two types of either v equal to 0 or v not equal to 0, but as long as it keeps direction and magnitude, that is equilibrium. Okay. However, that change in velocity is so minute that we cannot really distinguish. We cannot. It's very hard. I mean, we can measure it, but it's very small correction to everyday experience. So this building that I'm sitting in, and the building where you are at, can be assumed to be in equilibrium. The phone, for example, to a very good approximation right now, it's in equilibrium. Okay, although everything is shifting and moving, including the phone and myself and everything with it, but the correction that is coming from this acceleration due to the fact that we're changing direction is so small that you can assume that equilibrium is still valid. So this is not a bad deal here on Earth, okay? So, I mean, to give you an idea of why this is so, when you look at the horizon on the ocean, for example, you think that the Earth is flat and it's going forever. But you know the Earth is curved. As a matter of fact, when you go to the ocean, you're going to see the horizon, and that is actually the curvature where it's going to go. So the Earth is curved, but the curvature is so small that you can neglect it on a small scale. On a city scale, for example, it's very small correction, very minute correction. On 10-kilometer radius, for example, it's very small. On the house where I am at right now, it's even smaller than that. So it's so negligible that I can consider this as a flat surface. So this is on the Earth scale. So on a first order approximation, we can say we have these two types of equilibrium at v equal to 0 or with v not equal to 0 constant. Correct? So Sherry, you're right, okay? To this order of approximation. Everybody else also who agreed is correct too, okay? To this order of approximation. Yes? Okay, then we're going to talk about the support force, the kinds of forces. We're going to talk about dynamic equilibrium, that's what I was talking about, and the force of friction, which is a really nasty thing that we deal with, but in a sense also it's a beneficial thing that we will have to have. So sometimes friction is really something you don't want to have and you would want to minimize because it really works against your forces. But sometimes it's a necessary thing. Without it, we cannot move. I mean, I know we don't have icy conditions in Southern California, but if you live in somewhere where there is ice, on an icy day, for example, try to move the car. Sometimes it spins in place. So without friction, a car cannot really move. Without friction, you yourself cannot move. Actually, try to run in an icy conditions, you're going to find yourself going around in the same place. So without friction, we cannot do motion. As a matter of fact, what causes the car to move on the road, it's the friction itself, the force of friction itself. So the friction can be something that is not good. You would want to minimize it. For example, inside the engine, the moving part, for example, inside the engine itself, they have friction where the piston, for example, is rubbing against the wall of the chamber. That is friction. That leads to heat. That leads to waste of energy. So it needs to be cooled down. That's why you have to have oil in there to absorb that extra heat in there. Otherwise, the engine starts to overheat and melts and causes problems in there. That's not desirable. That's a problem. But the friction, for example, that is between the tire and the road to give traction to the tire, that is actually a necessary thing. Without it, the car will not move. That's why the tires for the racing cars, they have specific tires so that they can get more traction, so that they can actually move faster on the road and basically be the first. Okay, so that's some of the things that we need to know about friction. One of the things that we have to know about friction, and it's really not a choice in it, friction opposes motion. When I say motion, I mean velocity. So if the object is moving this way, friction is in the opposite direction. But what about this object in here? It's not moving at all. I'm trying to push it right now. I'm pushing it actually from here, and it's not moving. Then in this case, the friction is actually opposed not to the direction of motion, because this thing is not moving at all, but to the intended direction of motion. Had it moved, it would have moved in this way. So the friction will be in the opposite direction. So friction is a big topic. As a matter of fact, it complicates physics a lot, to the point that physicists gave it a name. It's the bad boy of physics. That's what they call it. Okay, so that's something that we need to understand. Then we get into the definitions of what the speed and velocity are. Speed is a number, is a scalar. When you're driving on the freeway, Highway 10, for example, and you call your friend and you tell them, you know what? I'm on the freeway. I'm going 50 miles per hour right now. Your friend will not be able, yes, you're really looking at the odometer and it says 50 miles per hour, but will not be able to tell which way you're going unless you give them the direction. That is what velocity is. It's that number plus the direction, which way you're moving. So the velocity is a vector. It's not a number. It's not a scalar. Scalar is just a number, okay? Then we have the concept of acceleration. The concept of the acceleration is the rate at which the velocity is changing. If you're gaining velocity, you're actually accelerating. That's what we day to day say. You're gaining velocity, that means you're accelerating. If you're losing velocity, you're actually decelerating. And you have to make a big distinction between deceleration and the direction of motion. You could be still going in the same direction, but the acceleration is opposite to it because you're slowing down, okay? So the velocity is pointing one way and the acceleration is pointing in the opposite direction. So those are some of the key concepts that we will be covering in this chapter. And I gave you more than actually their introduction. I gave you a little bit more into them than probably what this slide would have entailed. Again, I talked about Mr. Aristotle and his definition, his ideas. Any questions so far? No? This is the experiment I was talking about for Mr. Galileo. Basically, what he did was he took marble and he let it go from a certain inclination. And as the marble was going, it's going to stop at some point. You try this experiment at home, it's going to stop. No matter how steep this incline is, it's going to stop at some point. If you make the surface smoother though, if you go and basically refine the surface and fix it and probably put some, it's going to stop, but at a further point. And if you still make it finer and finer, you're going to have it basically a stop at very far distances. So that's why he concluded that if I have a situation where this surface is 100 or not interacting with my object, there is nothing to prevent my object from stopping, there is no reason for it to stop at all. It's going to continue forever and ever in the same direction with the same speed. So that was the basis of the first law of Mr. Newton later on. When Mr. Newton came on later on, he was born actually the day when the year when Mr. Galileo died. He summarized the work of Mr. Galileo in the first law of mechanics that later on he called it the law of inertia. So that's basically the idea from that. Nowadays, we can see clearly, we can probably understand or have a better view of this one in the time where we have access to all kinds of technologies, including space technology, where we can see actually objects moving. It was not evident there. You needed to convince people there at that time that this is actually the case. Now we know. Okay, he did all kinds of experiments. This was not the only experiment, though. This is another experiment famous by him also on the Leaning Tower of Pisa. He let go of different objects with different basically masses, different shapes. And he had shown that in the case of negligible air resistance, depending on the day, these objects will tend to fall in the same, again, same time. Doesn't matter what the mass is. Of course, if you tell me, okay, if I let go of a feather in here, it's going to go around before it falls, and that is because of the air resistance again. If you can neglect the air resistance or minimize as much as the air resistance, this experiment is true, okay? So he did all kinds of experiments. He argued this is another way of looking at the same experiment as before. Again, instead of doing a surface in here completely smooth and going forever and ever, you can actually have it so that it oscillates between the two surfaces. Obviously, the initial position and the final position will be the final position will be slightly less because of that thing called friction again. But if you smooth the surface as much as possible, this thing will oscillate. This thing will go back and forth forever and ever. But if there is a lot of friction, it's going to quickly die out. So that's basically what you can observe. So that's really what you need to do. If you make the surface as smooth as possible, it's going to oscillate for a long, long time. Furthermore, if this side and that side have the same inclination, that's fine. I mean, you can argue that this distance is the same as that distance. But if this inclination, for example, is this on this side is less on that side, it's going to travel a long distance as compared to the first one. Longer distance, at least. This side of the triangle is bigger than this side, okay? So proving that it's going to go for the same, basically, for a long time. And if you make this angle smaller and smaller, it's going to travel for a longer and longer distances before it's going to bounce back, before it's going to come back. So you don't really need to work a lot against the friction just by changing the inclination in here to prove that actually this is the same principle, that actually the friction is the one that is causing it to slow down to begin with, okay? So he made a lot of experiments and super smart, basically, experiments that enabled him to basically have that conclusion that it actually, the friction is the one that is causing objects to stop, and their property of the object, which is called inertia at that time, which is the ability of the object to resist the change in motion. That is basically, that is making the difference in here. So Here a question. I posted this stuff on Canvas, didn't I? Just to make sure. Because all of these questions should be there and the answers also to them should be there. Yes? No?
Yes, you did.
Okay, very good. So I'm glad you guys have it. So you have all of this material in there. I'm just going to be quickly going through it. So the use of an inclined plane for Galileo's experiment helped him to basically, the correct answer is C here, discover the property called inertia. Okay, that when he was convinced of different objects have different kinds of inertia, and that is the property inside the object that prevents it from changing its motion. That's basically what the key is. You guys agree that it's easier to stop, for example, a basketball thrown at you, let's say moving at 10 meters per second, which is about what, 30 kilometers per hour, which is about 20 miles per hour or something like that, than stopping a truck going 20 miles per hour. One of them has more inertia than the other one. Don't do this experiment at home, or at least do half of it if you want to. The basketball only, okay? Don't try to stop a truck because you're not going to be able to. It's you need more force than your hand, okay? So that's basically what the inertia is. So the inertia is related actually to the mass, the concept of mass. And the concept of mass is the quantity of matter in the object. The quantity of matter in object is what we call mass, and more mass, more inertia, less mass, less inertia. So there is this intrinsic connection between the two that people basically define inertia as being the mass, okay? But one of them is defined through the change in motion, and the other one is through content, basically, how much stuff it has in it. As a matter of fact, there is another component in here, and that is weight. The weight is, if you take an object and put it on a scale, it seems the same thing. You double the mass, you double the weight. So it is that one-to-one correspondence again, which is called the gravitational, basically, mass versus this mass. And this was a puzzling topic for physicists for a long, long time. It took the genius of Einstein to basically solve this puzzle. So inertia, mass, and the weight, basically, which is a force, the mass that is coming from that, or the measurement that is coming from the mass from there, they're all the same thing, okay? The weight is not a mass. The weight is a force expressed in different units, okay? Again, this is similar to an example I gave earlier about the truck. The weight and the mass are connected. They are not the same. The weight is a force, okay? You double the mass, you double the weight. So that's basically what it is. But an object, if you weigh it on Earth, it's not the same thing as you weigh it on the moon, for example, because the pull of the moon on the object is different than the pull of the Earth on the same object. And that is where the weight comes into play. So you have to make that distinction between the two. Okay, so Matt Damon, when he was trapped on Mars, he had to deal with the forces that are coming from Mars, not the forces from Earth. The pull of the gravity of Mars is less than the pull of gravity of the Earth. Okay. Again, mass and volume are also related to one another. They are not the same thing. And objects may have different volumes and different masses. Of course, if you double the mass of a given object, you double its volume also. Or you need to double it. When you double its volume. Oh, somebody likes the Mad. We're going to talk about that movie more, okay? If you guys have not seen it, and probably I will be talking about also the other movie, Interstellar, down the road when we talk about black holes toward the end of the class. Okay. So, the mass and the volume are related concepts, but they're different. One of them is actually measuring the physical properties of the object, which is basically the space it takes in the amount of space it takes, basically, and that's the volume. And its unit is cubic meters, and the mass is expressed in terms of kilogram. Every time I mention units, they are in the standard measurements of standard so-called SI, le Système International, which is the international system of units. So I'm not going to be using non-standard units. So the mass is in kilogram, the volume is in a cubic meter, because the meter is actually a fundamental unit, but the volume is measured in a meter times meter times meter. So it's a meter, 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 or a cubic meter, okay? Again, the concept of inertia mostly involves mass, that's it. The weight has nothing to do with the inertia. That's a force, actually. And the volume is actually has nothing to do with the mass. So the mass is the key concept in here for this answer in here. Okay. So this is the standard unit for kilogram, which is the unit that people have agreed on Earth as being, this is the standard fundamental unit. They agreed on a certain material and they put it in a museum in Paris, and later on they created replicas of that, and they said, this is it, this is the standard. Because if we have different standards everywhere and we don't know what we're doing, then it's going to be a problem. So we had to agree on something. Is it right or is it wrong? That's a key question that we usually ask. My question is, for example, if we meet aliens tomorrow from a different planet and a different thing, they may have it different. They may have come up with a different convention for a kilogram, for example, for their unit of mass than our unit of mass. There is nothing fundamental about the kilogram, by the way. It's only us that we agreed on it in here on Earth, that this is it. This is with which we're going to compare everything, because measurements involve comparing with something, with a standard, and the standard we agreed on is the kilogram. Okay? Of course, the answer to this question is it's neither right, neither wrong. I mean, it's just a convention. It's just an agreement that people agreed on. Okay? So there is no real reason for it to be that much other than the fact that it was a convention, so that people will have some standard with which to compare things to.
I think if we meet aliens, we have bigger problems than worrying about the kilograms.
Okay. We're gonna resolve everything, and we're gonna talk about the kilogram, because I'm gonna give this example a lot, okay, about the aliens. Okay, we're talking now about the nearby star, namely Alpha Centauri, Proxima Centauri, having several planets, Earth-like planets. And although now there is the new research indicate that there is no way that at least a carbon-based life could exist there, because of the fact that Proxima sends X-ray radiation to regular basis and will kill anything that is carbon-based. But if in case there are basically intelligence life in there and we'll be able to communicate with them, there are all kinds of things we will ask them basically, and they will ask us and try to communicate, and one of them is the kilogram, okay? Okay, this is a question that was asked basically, and the answers also is in there. So if you pull it slowly, which side is going to break? Of course, it's the top one, and that is because the force of the pull from your hand and the weight combine, and there will be stronger force on this side than on this side, okay? So that's why the top will snatch. But if you do it the other way, if you go fast about it, it's actually the lower part is going to change, and that is because of the inertia of this mass in here. Try it at home, especially since you guys bring something massive, and don't hurt yourself for doing that, and it should work, okay? The concept of density is an intrinsic property of objects. If you take a mass divided by the volume, this is a quantity that you're going to identify the objects with. Basically, this is unique to every single quantity that we're going to be dealing with. When we talk about the solar system down the road, which is toward the end of the class, we're going to be identifying that this is a key unit that we identify the structure of different planets. So when we find the density, we will know this is planet is made up of such and such material versus this planet which is made up of such and such materials. And by the way, the Earth is the densest planet in the solar system. So those are some of the questions that are, if the density of 1 kilogram of iron is the same everywhere you go. Okay, so it doesn't matter, because we're not measuring the mass. We're not measuring, I'm sorry, the weight. We're measuring the mass and dividing it by the volume. Okay, as long as these two don't change, you're fine. It's the same thing. Well, when objects are under different forces, they tend to be basically the sum of the forces, or the net force is the one that is going to be where the object moves. You have to remember something in here, very, very important, and that is the force is also a vector. So if I'm pulling on one side and I'm pulling in the opposite direction, it's the difference between the two that matters. But if I'm pulling in the same thing, it's the algebraic sum, because this has a magnitude and direction. And if I'm pulling at this direction and I'm pulling at that direction, the force is actually the resultant. So it's like so where the sum of these two vectors, it's a vector sum. So it's really a concept that has to have both magnitude and direction, just as velocity, as I mentioned in the beginning, has both, okay? And again, you have an object moving, being pulled by 15 Newton force on one side, and to the left with 20 newtons, and the correct answer in this case is different. You are pushing it 15 newtons on one side and 20 newtons on the opposite direction, so it's the difference. 20 minus 15, it's 5 that wins on this side. If I pull it 15 and 15, the object is not going to go anywhere, because the 15 and the 15 cancel, okay? That's what people play when they pull ropes together and when they're playing on those things. Now, so that's a concept in here that you guys need to understand, okay? One thing about the unit of the force is in Newton, and Newton is not a fundamental unit. The Newton is a combination of the meter and the kilogram, and also the time. Okay, that's correct. Thank you. So left. The correct answer is going to be left, because everyone's asking about the question. Did I say it wrong? 15 to the right, 20 to the left, 20 will win. Oh, because of probably the way the image is flipped around in here and on Canvas, okay, on Zoom. So my left looks right and my right looks left because of the, sorry about that, okay? Yeah, you guys need to, so if I say right, probably it looks left to you guys, so because of the image is flipped and on there. Okay, so the bigger wins, whichever way it is. So if it's left, it's left. If it's right, it's right. Okay. The condition of equilibrium is all the forces must be canceling. Okay. There is another condition that we're going to learn later on, and that has to do with the twisting motion. An object needs also to be canceling all the twisting forces, which are called torques or moments. And then also, for the case of linear motion, it's the forces. The sum of the forces have to cancel out for the object to go nowhere. So in the case back onto my phone, it's being pulled by the ground, but my hand is pushing it up. So in this case, it stays in its place because these two forces cancel one another. Okay. So that is the condition of equilibrium. This is a vector quantity. These are not, again, scalars. Forces are vectors. So the correct answer is A. Dynamic equilibrium, an object that moves at constant velocity is in equilibrium. That's what we said in the beginning. So you could have equilibrium where the velocity is 0, like in the case of this example. This is not going anywhere, at least vertically, okay? People can move around back and forth, but what we're concerned about in this case is the vertical motion. And in this case, actually, you can have equilibrium when you put the cruise control on the car. Technically, the forces are canceling so that you're moving at constant speed, basically. Okay, so that's really the idea in here. So a bowling ball is in equilibrium when it's at rest or moving at constant speed. That's the same thing. Okay. The support force, again, is what I called earlier the normal force. It's normal because it's perpendicular to this force, to the space. If there was no support force from my hand, this phone should fall. Okay, but it did not fall because of that support force in there. We have about 25 minutes, so we're still good. We still have time. Okay, we should be good. So when you stand on by the way, the support force is exactly what you measure when you go on the scale. You don't measure anything else. So when you read your weight on the scale, that's what you're actually reading is the support force, the normal force that is exerted by the scale back on you, because you're standing on the scale. the scale has to push back to stay in its place. So it tells you this is how much I am pushing back. So if you're, for example, on an elevator and you are on the scale, and if the elevator takes off, the reading on the scale will be less because you're accelerating upward. Or is it? More, I'm sorry. Because you're accelerating upward, your inertia now is going to push backward. So in this case, actually, is going to be more force on the spring, on the springs of the scale. So the scale has to push more. So actually, you feel it in yourself too. You feel that you're dragged down. You feel heavier when the elevator takes off. When the elevator is about to stop, it slows down. So your inertia again keeps you moving upward, which makes it that you feel lighter. Actually, you feel kind of, oh man, we're coming to a stop now. You feel yourself lighter. And the scale in this case will be less because you're pushing less on the scale. So your weight, instead of reading, for example, if we're doing it in pounds, instead of reading 170 pounds, it may read, let's say, for example, 162 pounds or something. All of a sudden, you lost 8 pounds. Just because you're coming to a stop by the scale, by the elevator. But when you're taken off, instead of reading 170, it may read 182 or 180 or 178 or something, depending on the acceleration with which the elevator takes off or slow down. So that's the thing that you're measuring. So you're measuring the reading that is the support force. That's what you read. You don't read directly the weight, okay? So that's really the idea behind it. I have an idea, guys, for you guys. Anybody interested to go in business with me? Can I have some volunteers to start a new business? Nobody?
What kind of business?
In the weight loss business.
Weight loss, okay.
Yeah, I have, in the beginning of the year, guys, Avery is also, okay, in the beginning of the year, people promote all kinds of solutions for losing weight. Here is my suggestion, okay? And you go and start it and collect money beforehand, okay, for the people who want to lose weight. They lose as much weight as you want them to lose. Put them in an elevator, cut the strings and let them fall, and they will be weightless. Isn't this good?
That's terrible. Weightless and dead.
That's why I told you guys to collect the money beforehand, okay? Okay. So again, just to talk about the fact that this is, oh man, what happened to my screen? That the force of support force is the one that actually measures your weight on the strings and on those devices in there, okay? Then we talked about the force of friction. It's a resistive force, okay? Microscopically, it's really where the two materials meet, okay? And that is the interaction of the different atoms from one object to the other one. It's a very complicated process through which this interaction happens. Macroscopically, we can experiment it. We can see it on a regular basis, okay? Like I said, and in icy conditions, it's very hard to move, okay? The force of friction occurs everywhere. So that's really the thing with it, okay? That's, you have to be in empty space for the friction not to be there. That's why it's really, in this example in here, she's pulling at constant speed, pushes across the floor at constant speed. So her force must be exactly equal to that of the force of friction for it to happen. Okay, so there is friction there in the case of motion. Okay. And then when it's increasing speed, she needs to overcome friction and pushes more than that with which, so in this case, the correct answer is going to be less than, the force of friction should be less than that of hers. Okay. Is this correct? Do you guys agree? Okay, good. I already agree.
I read the question wrong.
Okay.
My
Okay.
fault.
No problem. Okay, so by the way, guys, don't hesitate to ask questions, okay? Because we're going quickly through these materials, and I want you guys to have to be at ease with it, okay? The concept speed, again, is just defined as the distance covered over the time traveled. It's really two measurements. You need to find the position at some time and another position at a later time. So you need to do two measurements. Measure the position at an initial time and the position at a later time, and find the difference between these two positions. That's the distance traveled. Over the lapse of time that has occurred between the initial time and the second time, that is your travel time. Divide these two quantities and it's going to be your speed. That's exactly what your speedometer does all the time. When you look at it and it tells you the speed is 49 miles per hour, a second later it's going to be 50 miles per hour, a second later it may be more or less depending on how you're doing your driving. That is what it's doing all the time. It's making two readings each time to give you those numbers. So that's really, it's doing it so fast though, but it's really the concept behind it. You need two measurements. The unit for it is a meter per second in the SI. People use miles per hour, use kilometers per hour, use all kinds of different units, but the fundamental unit for it is meter per second. The average speed is the distance covered overall divided by the average time. For example, it may take me, I leave home, go to work, and come back home. On average, I did not travel. So my average distance in this case is 0. So on a daily basis, if I just want to average these things, I have a 0 distance. I go around, move back here and there, and then come back. So the average speed is different than the actual speed, or the so-called instantaneous speed, okay? That's what your speedometer is doing. If you look at it every single moment, it's giving you as close as possible from your instantaneous speed, okay? Okay. The average speed of driving 30 kilometers an hour is the same average speed as driving 60 kilometers divided in 2 hours, because 60 divided by 2 is the same thing as 30 divided by 1. Again, this is the first point that everybody has raised, including Sherry and everybody else who agreed with her, on the fact that motion is relative and everything is moving with respect to everything. So there is no really a standard frame of reference that you can call this is where everything is sitting still. Nothing is that. However, there is every object while it's moving has its own frame of reference, which is called the proper frame of reference. For example, if I'm sitting in the car and moving, as far as I'm concerned, somebody is pulling the whole road behind me and the whole scenery behind me. As far as I'm concerned, I'm sitting. Actually, I have my cup of coffee next to me and nothing is happening. So as far as I'm concerned, I have equilibrium and everything, or not equilibrium properly said, unless I'm doing at constant speed. And everything else is zooming past me on the opposite direction, okay? So the concept of acceleration again was due to Mr. Galileo, who's the one who did all kinds of experiments, and that is the rate at which velocity is changing over time. The word rate involves a ratio, involves a fraction. Okay. Again, just as much as we did earlier, find the velocity at which is the difference between two measurements involving distance, involving positions at different times. The same thing with the acceleration. You measure the velocity at some point, you measure the velocity at a later time, and you divide the difference between the two velocities over the lapse of time between them. So that's basically what this concept is. The unit for it is the unit for velocity, which is meter per second for every second. So the unit for it is meter per second, or symbolically, you do also meter per second squared. That's also another way of expressing it. So the pull of the Earth on any object, this one, for example, is 9.8 meter per second. That is what Mr. Galileo has actually measured for us, okay? Okay. The free fall is in case where an motion is subject just to the force of gravity. Like this one, I can approximate it to a free fall. It fell all the way down, okay? So all of these questions are related to that. And this is the data related. Okay, when an object falls freely, you have to understand that it's gaining 9.8 meter per second for every second. Or 10 meter per second, approximately 9.8 is 10. 10 meter for every second. So if it was moving, and there are several questions in here, since we have time, we can actually go and cover them. Here is a question. If a falling object gains 10 meter per second, each second it falls, its acceleration is, so the units of the acceleration as meter per second, not meter per second. Actually, symbolically, we can write it also, and this is what you will see. Come on. You can write it also like this. Meter per second squared. So you might see this unit in there, okay? Or meter per over second per second. So that's symbolically. The 2 there indicates that you're doing the time twice. So that's the unit for it. So the correct answer should be B. Okay. Free falling object has a speed of 30 meters per second at 1 instant. Exactly 1 second later, its speed will be, of course, it's gaining speed. So when its object has already 30 meters per second, later is going to be moving faster. 1 second later is going to gain another 10 meters per second or 9.8 meters per second. So the correct answer is not the same speed, it's accelerating. It's not 35 meters per second, actually it's more than that, because we know that it's coming down with 30 meters per second and it's going to gain almost 10 meters per second, and 35 meters per second is not enough in that 1 second. So it has to be more than 35, and the correct answer is 35 meters per second. It's not 60 meters per second, that's too much. That you would have gained about another 30 meters per second, and that is 3 times the acceleration on Earth, and that is almost the acceleration on Jupiter, which is too much of an acceleration on Earth in here. So the correct answer has to be C in this case. More than 35, but less than 60. It's actually around 40, 39.8 to be more specific, meter per second. Okay. The distance fallen by free falling body remains constant. It's not constant because the speed is increasing. So the distance covered every second has to increase with the speed. So it's not constant. Increases each second when falling. That's the correct answer, because the first second it may have dropped this much. The second probably has dropped this much. The third second will drop this much probably. Okay. So if the initial second was, let me try, is there a drawing tool in here? Yeah, draw. So the first time is this much. This is the first second, the second. This is between the second and the third. This is probably between the third and the fourth. And the last one I cannot draw it because it's way bottom. So this is the distance is increasing because the velocity is increasing, okay? So that's what you need to understand about this concept in here of the free fall, because the acceleration is not 0. Had the acceleration been 0, then it would have traveled the same amount of distances between every 2 seconds. I intend to have this distances to be the same distance covered, okay? This is not true, okay? And so increases each second. So this is some data in here representative of some free fall of an object at t equal to 0. The initial velocity is 0, so the distance traveled is 0. 1 second, it has traveled 10 meters. The distance in this case has this expression in here. The distance, I don't know if you have it there. Let me see if my pen works in here. Okay. Yeah. The expression, come on, 1/2, okay, it's not writing. Control Z, looks bad. So, this is the mathematical expression that is actually behind the scene, okay? If I ever can get it to work. Cannot do it. Wow. Let me leave this thing in here.
Can you try the text box at the top? Do you see that?
Hold on. The acceleration, which is the symbol for it, is g. That's the 9.8 t squared. So that is the underlying law that is there, okay? That's why after the first second, 1 times 1, that's the t squared. So that's going to be 1 squared. G is 10, approximately 10. 10 divided by 2 times 1 squared is 5. So when you look at the table again, That's the 5, where the 5 is coming from. Okay, let me stop sharing this thing in here and go back to the slide. So that's where that 5 is coming from. It's coming from 1/2 times 10 times 1 squared. 1 squared is basically a 1 times 10 divided by 2, that's 5, okay? After 2 seconds now, 2 times 2, that's 4. 4 times 10, that's 40 divided by 2. 40 divided by 2 is 20. You guys understand where that formula is coming from, where these numbers are coming from? Now, after 3 seconds, let me go back into that and try it on 3 seconds. We should find 45. After 3 seconds, this will be 3 squared. 3 squared is 9. 9 divided by 2, 9 divided by times 10 first, because this is 10, that's 90. 90 divided by 2, that's where the 45 is. So that's where 45 is coming from. Okay? 45, what do you mean? That's the 45, the distance traveled. Now, if we try this now for, what is it, 4, we should find a difference. 4 squared is 16. 4 times 4 is 16. Times 10, that's 160. Times 1/2, 1/2 times 160 should be 80. Let's go back into the table. So after the 4th second, the distance is traveled is 80. Now after the last second, which is in this table, 5 times 5 is 25. Times 10 is 250. 250 divided by 2, that is 125. Do you guys understand where these numbers are coming from? The underlying law in here for this table is this formula. 1/2 g, which is 10, times t squared. So that is the law that we're using in here to try to understand the free falling bodies and how they fall. Okay. Okay. Do you guys have any questions? So it's very important that you guys have to do the initial exercise that you guys have. And Sarah, if you don't have access to it by the end of the day, please let me know. Probably by noon or so. Let me know. I will send you another code and try that code. Okay.
I tried adding myself again and it worked, so I'm added to the class.
Okay. Very good. Very good. So I think it's going to work for everybody else too. Very good. So I guess I'll see you guys on Thursday at 8 o'clock. And have a safe rest of the day. And you can send me questions on Canvas all the time. That's the preferred way of doing business, okay? It's through Canvas inbox. Thank you.
Thank you. Bye.
Bye.
Thank you. Bye.
Have a good day.
You too, guys.